We are in Chapter 8, Further Applications of Integration. Section 8.1 is arc length. Arc length is the length of a curve. To determine the length of a continuous function, y equals f of x on the interval from a to b, assume the derivative is also continuous on the interval, and divide the interval into n equal subintervals, each of width delta x, and points pi. You can see this in the picture on the right. The curve can be approximated by a series of straight lines connecting the points. The length of each line segment is p sub I minus 1 to p sub I, and the length of the curve is approximately the sum of all these pieces. A better approximation can be found by taking n to be larger, so meaning that we'd have more of those little subintervals. And so we'd have the limit as n approaches infinity of the sum of that distance between p sub I minus 1 to p sub I. So we're going to define delta y as a change in y. So we'll say y sub I minus y sub I minus 1. And again, y's are also defined by f's. So we'll say f of x sub I minus f of x sub I minus 1. And similarly, this would be true for x. So we'll say down. And similarly for delta x, so that change in the x values, the length of each segment, and we'll say the length from p sub I minus 1 to p sub I is going to, using the distance formula, would be the square root of, and we'll have x sub I minus x sub I minus 1 squared plus that distance in y, which is going to be y sub I minus 1 squared, which is also the same thing as just saying delta x squared plus delta y squared. By the mean value theorem, we know that on the interval of x of I minus 1 to x of I, there is a point x of I star, so that f of x of I minus f of x of I minus 1 is equal to the derivative at that point times x of I minus x of I minus 1. This is similarly can be written as delta y equals f sub prime of x of I star times delta x. Therefore, the length can be written as, so we had defined it up above as delta x squared plus delta y squared. Substituting in what delta y is as defined up above, this is going to equal the square root of delta x squared plus f prime at x of I star times delta x all squared. This would be equivalent to, say, delta x squared. Pulling that out, we'd have 1 plus f prime of x of I star squared. So this would be equal to, we'd have the square root of 1 plus f prime of x of I star squared times delta x, pulling that delta x out of the square root. And since we know the length, as defined up above, would be the limit as n approaches infinity of the sum from I equals 1 to infinity of each segment, which is p sub I minus 1 to p sub I. This is going to equal the limit as n approaches infinity of the sum from I equals 1 to infinity of, and we just defined that distance with the radical expressed up above. So this would be the square root of 1 plus the derivative at x of I star squared delta x. So using this, we have arc length formulas right below, and says if f prime is continuous on the interval from a to b, then the length of the curve y equals f of x on the interval from a to b is going to be defined as L equals, and rather than having the limit of the sum, we're going to rewrite this as an integral, since we're dealing with a continuous function here, from a to b of 1 plus f prime of x squared dx. And again, arriving at that from the formula that we just derived. Likewise, it says if g prime is continuous on the interval from c to d, then the length of the curve x equals g of y, and the y is in between c and d, will be defined as L equals the integral from c to d, the square root of 1 plus g prime of y squared dy. So the examples on the next page say find the exact length, so we will be integrating, not using the sum notation. So find the exact length of the curve. And this is going to be for parts A through C. So part A says y squared equals 4 times x plus 4 to the third. X is in between 0 and 2, and y is greater than 0. So the function that we have right here, we're going to isolate y first. And so we would say that y is equal to the square root of, and it's 4 times x plus 4 to the third power. And rewriting this, we can rewrite this as square root of 4 would just be 2 times x plus 4 to the power of 3 over 2. And in order to calculate the length, we're going to use the formulas that we just wrote down, which is going to be the integral from a to b of square root of 1 plus the derivative squared dx. So in order to do this, we need the derivative. We need our dy dx, or our f prime. And taking the derivative of this, we have 2 times, it's going to be 3 over 2 x plus 4 to the 1/2 times the derivative of the inside, which is just 1. And simplifying from here, we get 3 times x plus 4 to the 1/2 power. And now, in order to do this problem, the inside, my integrand is going to be the square root of 1 plus f prime of x squared. So I'm going to rewrite this first, and then I'll evaluate the integral. That way I can simplify it. So it's going to be the square root of 1 plus the derivative squared. So we're going to have the square root of 1 plus, and it's going to be 9 times x plus 4. And then from here we can simplify this a little bit more, and we're going to arrive at the square root of, we're going to have 9x, and then 9 times 4 is 36, plus the other 1 would be 37. So now, in order to calculate the exact length of the curve that we have, with x being between 0 and 2, we're going to have to integrate this from 0 to 2 of the formula that we have for that length, which is going to be 9x plus 37 dx. And to integrate this, you can't do this as it's written, so we're going to let u equal 9x plus 37, du would equal 9 dx. And so rewriting our integral, again, I do need to change those limits of integration. I'll do that momentarily, but we're going to have 1/9 times the square root of u, or u to the 1/2 du. And our upper limit of integration is going to be 9 times 2 plus 37. So 18 plus 37 equals 55. So that's going to be our new upper limit of integration. And our new lower limit of integration, substituting in 0, we have 9 times 0 plus 37. So lower limit is going to be 37. So from here, we can easily integrate this. And so we have 1/9 times, adding 1 to our exponent, we get 3 over 2. multiply by that reciprocal, and evaluating this from u equals 37 to 55. And so from here we get 2 over 27, and then we would have 55 to the 3 over 2 minus 37 to the 3 over 2. This answer is also correct. If you wanted to, you could definitely rewrite this and say this is 55 times the square root of 55 minus 37 times the square root of 37. Same answer, just a different way to rewrite it. The next example says x equals y to the fourth over x plus 1 over 4y squared, and y is in between 1 and 2. So this time you'll see that we're going to be finding that length, not with respect to x this time, but with respect to y. And so in order to do this, we first need to take a derivative. So our dx dy, and then taking a derivative with respect to y, we're going to end up with 4 over 8 y to the third. This second term right here is the same as 1/4 y to the negative second. So taking a derivative of this, we're going to have the plus 1/4 times negative 2y to the negative third. And just kind of cleaning this up a little bit, we have 1/2 y cubed minus 1 over 2y to the negative third. And then from here, I have the square root of 1 plus dx dy squared. And so rewriting this, I'd have 1 plus 1/2 y cubed minus 1/2 y to the negative third squared. And multiplying this out, we have the square root of, it's going to be 1, and squaring that second part, we end up with plus 1/4 y to the 6 minus 2 times 1/4, those y's would cancel, which is nice, plus 1/4 y to the negative 6th. So again, cleaning it up from here, the square root of, and I'm going to have 1/4 y to the 6. Simplifying the 1, and this is negative 1/2. We have plus 1/2 plus 1/4 y to the negative 6. And if you realize that actually is very similar to what we had over here, because remember that was negative 1/2, and what we had up here. So you could actually factor this. It turns into a perfect square. And so this is going to be the same thing as 1/2 y cubed plus 1/2 y to the negative third squared. And so this simplifies even from here more, but I'll go ahead and rewrite my length formula here to find that arc length. And so we're going to be integrating, since we're integrating with respect to y, it's going to go from 1 to 2. What we have here is the square root of the derivative squared plus 1, which worked out to being 1/2 y cubed plus 1/2 y to the negative third squared dy this time, since we're integrating with respect to y. The square root and the squared would reduce out, and so we have the integral from 1 to 2 of 1/2 y cubed plus 1/2 y to the negative third dy, which we can easily integrate. And so integrating this, we have the 1/2 out in front times 1/4 y to the fourth plus 1/2 times negative 1/2 y to the negative second. And we'd be evaluating this whole thing from y equals 1 to 2. Cleaning this up a little bit before we evaluate it, we end up with 1/8 y to the fourth minus 1 over 4y squared. And again, this is evaluated from 1 to 2. So first substituting in the 2's, we end up with 1/8 times 2 to the 4th minus 1 over 4 times 2 squared minus, and then substituting in 1, we have 1/8 minus 1/4. And working this out, we end up with 2 minus 1 over 16 minus 1/8 plus 1/4, which simplifies to 33 over 16. So this is the length of the curve from y equals 1 to 2 of x equals y to the 4th over 8 plus 1 over 4y squared. So we have two examples here. The first one we were integrating with respect to x. The second one we were integrating with respect to y. So take a second to look at those differences. And then also circle part C, and we're going to complete this one together in class. So at the top of the next page, it says arc length function. If a smooth curve C has the equation y equals f of x from a less than or equal to x less than or equal to b, let s of x be the distance along C from the initial point, which we defined as p sub naught, which is at a f of a, to the point Q, which is at x f of x. Then s is the arc length function, so this would work for any 2 points, say an initial point and x. So we're going to say s of x would equal the integral from a to x of, and again it's the square root of 1 plus the derivative, and I'm going to call it evaluated at t squared, and then dt. So this would give us a function that would allow us to evaluate it for any length. So maybe from just 0 to 2, or 0 to 4, or 0 to 9, whatever it is that we wanted to. So the example right below this is find the arc length function of the curve y equals ln of sine of x from 0 less than or equal to x less than or equal to pi with a starting point of pi over 2 comma 0. And it does tell us it wants an arc length function. So in order to do this, again, we still need that derivative. So dy dx. And I know that we are going to be integrating with respect to x. And so dy dx is going to be the derivative of natural log of sine of x is going to be 1 over sine of x times the derivative of sine of x, which is cosine of x, which this is going to be cosine over sine or cotangent of x. And so our function, and we'll call this s of x, like above, is going to be the integral from a to x, the square root of 1 plus that derivative at t squared dt. And so for us, we're going to be going from a to x, and a is our starting value, and our x starting value is pi over 2 to x, and it's going to be the square root of 1 plus, and then we're going to have cotangent of t squared dt. So 1 plus cotangent squared t. We can rewrite that using our Pythagorean identities as cosecant squared t dt. And the square root of cosecant squared t is just going to equal cosecant of t dt. And we can integrate this, and when we do, we get the natural log of the absolute value of cosecant of t minus cosine t, evaluated from t equals pi over 2 to x. And so from here, substituting in x, we're going to have the natural log of cosecant of x minus cosine of x minus the natural log of cosecant of pi over 2 minus cosine of pi over 2. And so simplifying this a little bit more, we have the natural log of cosecant of x minus cosine of x minus, and cosecant of pi over 2 is just equal to 1, and cosine of pi over 2 is equal to 0. And so 1 minus 0 is 1, and the natural log of 1 is just going to be 0. And so therefore, we can say that our function, s of x, is just going to be equal to the natural log of the absolute value of cosecant of x minus cosine of x. So what this allows us to do is, given this curve, we can find the exact length of it. Starting point is going to be pi over 2 comma 0, but to any length of x. So whatever x is going to, again, we are limiting it between 0 and pi, but if we wanted to go to 3 pi over 4 or something along those lines, we'd be able to evaluate that easily with this function.